Welcome to CSAI Think Tinker Learn. Today, we are moving into domain 3 of our System Design Essential series, the data layer. Specifically, we are breaking down relational schema architecture, the master blueprint. The series is designed to give you a solid mental model of complex system design topics at a very high level. Before we jump in, please, if you like this video, hit that like button, share this video, and subscribe to support the channel. You can find the full technical articles and a diagram on our companion site. The link will be in the description, but this is the site for the GitHub pages. The articles are listed here. Currently we are starting with this article, so this will be our main article today. And if you're more interested in other sites, then I'll have another site, bitbytoken.com. The link will be in the description again. Okay, now specifically about this series, these videos are kept very short to provide a general framework. If you want a dedicated deep dive on any of these things, like a B tree rebalancing or any other BCNF math, let us know in the comments and we'll definitely make a video for that. Okay, let's deconstruct the physics of data. Okay, now every database starts as a monolith or zero normal form. This is just a flat file where we dump everything. It seems convenient initially, but it is a trap. If an author writes 100 posts, their email is repeated 100 times. This leads to update anomalies. If that author changes their email, you must modify every single row. If you miss just one, you have created a fatal data inconsistency. This relies on a brute force storage and lacks any real constraint enforcement. The first normal form is our Atomicity engine. It demands that every column holds only indivisible values. A common junior mistake is storing arrays or comma-separated tags within a single string cell. This is a failure point because it forces the CPU into expensive string parsing operations during every query, completely neutralizing the database ability to index or filter that data efficiently. One NF or one normal form requires a primary key to uniquely identify every atomic row. Now, second normal form or 2NF focuses on full dependency enforcement. This is strictly for tables that use composite primary keys. 2NF eliminates partial dependency, where a non-key attribute depends on only part of the composite key rather than the whole thing. If a product's name is stored inside an order item table, a change to that product name forces an update across every historical order. 2NF forces you to move that data into a dedicated products table. Third normal form and BCNF are about transitive eradication. We want to break chains where A leads to B, B leads to C. For example, in a student's table, if the student determines their major and the major determines the advisor's phone number, the phone number depends on the students only indirectly. This allows for a data drift. If you delete the student, you might accidentally delete the advisor's phone number from the entire system. We eradicate these indirect dependency by identifying all candidate keys early. Now a senior insight. Normalization is for integrity, but sometimes we need speed. This is the denormalization trade-off. In read-heavy OLAP or analytics environment, complex multi-table joins are too heavy. We intentionally introduce controlled redundancy to pre-join tables. The massive failure point here is data synchronization. By storing the same data in multiple places, you risk inconsistency. You must enforce sync via database triggers, materialized views, or robust application layer logic. Before you write a single line of SQL, you need a schematic, the entity relationship mapping. This is your city's planner's sketch. Entities become tables, attribute becomes columns, and relationships are enforced via foreign keys. A critical failure point is mapping cardinality incorrectly. Forgetting a dedicated junction table for many-to-many relationship will physically break your data insertion path. The database engine's internal enforcer guarantees referential integrity across these cyan tethers. Without indexes, a database is blind. It must perform a sequential scan, physically reading the entire table from disk, from top to bottom for every single query. As your table grows to millions of rows, this creates a severe I/O bottleneck that blocks all other system operations. In this state, your execution speed is directly tied to the physical read limits of your underlying storage hardware. We need a way to skip the line. The B tree and the B plus tree are the default express lane for relational databases. B trees store keys in sorted order, allowing for logarithmic O-log and traversal. B plus trees makes it a step further by keeping data pointers in linked leaf nodes, making range scans like using between or greater than incredibly fast. The trade-off is rebalancing overhead. Every time you insert massive amounts of unstructured data, the tree must split and rebalance, which can drag down write performance. For lightning fast exact matches, we use the hash index locator. A mathematical hash function maps a key directly to a specific bucket, providing O1 average lookup speed. This is perfect for session IDs or UUIDs. However, the failure point is structural. Hashing completely scrambles the data ordering. A hash index is useless if you need to perform a range queries or sort your results. It is an exact match only tool. When dealing with low cardinality columns, columns with few distinct values like status flags or boolean types, we use the bitmaps. It creates a bit array for each value, and multiple conditions can be combined via CPU-friendly bitwise operations. This filters millions of rows constantly and instantly. But beware, high cardinality data like unique timestamp will create massive sparse bitmaps that are catastrophically expensive to store and very slow to update. Here is the index selection protocol matrix. Choosing an index is a strict engineering trade-off. B trees are for range and equality with moderate overhead. Hash indexes are for exact matches with low overhead but no sorting. Bitmaps are for low cardinality with fast bitwise reads but high write penalties. Misapplying these, like putting a bitmap on a primary key, will aggressively degrade your throughput and cause deadlocks. A covering index is the ultimate read optimization. It includes all columns required by a specific query, allowing the engine to satisfy the request without ever touching the actual table data. This is called an index-only scan. This vastly reduces I/O. The catch is the write penalty. Every insert or update must now modify the table and every single attached index. Over-indexing will eventually cripple a write-heavy system. To build up like a professional, follow the master engineering protocol. Gather requirements, draft the ER diagram, map the relational schema, normalize to 3NF, identify access patterns, and finally deploy targeted indexes. Failing to plan for schema evolution and hard coding rigid structures without a migration path guarantees catastrophic technical debt. Use tools like Flyway or Liquibase to version your blueprints. In modern engineering, we often use object relational mappers like SQL Alchemy to prototype these designs in code. But remember, design like an architect, but measure like a scientist. A major failure point is blindly trusting ORM generated SQL, which can easily hide sequential scan and catastrophic bottlenecks. Now, for the community, what is the most complex N plus 1 query problem you have ever had to solve with custom indexing? Let us know in the comments below. If you like the video, please like, share, and subscribe to CSAI Think Tinker Learn for more system design essential. Until next time, thank you for watching. Bye.